So imagine this. You have to build a critical supply base in one of the most hostile places on the entire planet. And I'm not just talking about the weather. I'm talking about the terrain, the geology, and yeah, an active conflict zone. How on earth do you find that one perfect spot where your entire project won't get washed away, buried in a landslide, or spotted by the enemy?
I mean, just look at this landscape. This is the challenge, right here. The Himalayas don't forgive mistakes. Picking the wrong location isn't just a costly error, it could be a total catastrophe. So how do you sort through thousands of square kilometers of mountain to find that one safe, stable, and truly secure location?
And the stakes here? They couldn't be higher. We're talking about a logistics hub, a place for fuel, ammo, supplies, the works. This isn't just some civilian construction project. It has to be tough enough to survive the elements and smart enough to function under the constant threat of conflict.
So, how do we do it? Well, the solution is this really fascinating process of elimination. You can almost think of it like a detective story, but told with maps and data. We approach the whole problem with a 3-layer model, systematically filtering out all the bad locations until only the perfect ones are left standing.
Okay, so here's our framework. It boils down to 3 fundamental questions. First off, can we even physically build anything here? Is the ground suitable? Second, if we build it, can it withstand the immense power of nature in the Himalayas? And finally, is it tactically secure from enemy threats? Each one of these questions is like a layer in our digital sieve.
So our investigation kicks off with the most basic question of all. Let's forget about everything else for a second. Can we physically build a solid structure right here? This is all about the ground itself.
The very first filter, and it's pretty obvious in a mountain range, is the slope. I mean, if the ground is too steep, your costs just explode. The risk goes way up, and even moving vehicles around becomes a total nightmare. So you have to draw a line in the sand.
And check out how ruthless this rule is. For a major hub, any location with a slope greater than 10 degrees is immediately tossed out. Gone. It's just not feasible. And with that one simple rule, huge parts of the map are instantly eliminated from our search.
Now here's a detail that is so crucial but so easy to overlook. Which direction does the slope face? A north-facing slope in the Himalayas gets way less sun. That means snow and ice hang around for much longer, creating this freeze-thaw cycle that just destroys roads and can shut down a supply line for months. It's a logistical killer.
Okay, so we found some relatively flat spots. But now we move on to layer 2, where we have to ask a much scarier question. Will Mother Nature even allow a building to exist here?
You know, one of the biggest hidden threats is water. And I'm not just talking about flash floods. I mean persistently waterlogged ground. If the soil is basically a marsh or acts like a sponge, it can't support the heavy foundations of roads or bunkers. It's this invisible threat that can undermine absolutely everything.
So to find these hidden wet zones, we use this really clever tool called the Topographic Wetness Index, or TWI. It analyzes the terrain to predict exactly where water is going to pool, long before you'd ever see a puddle. It's kind of like giving the landscape a hydrological X-ray.
And this leads to another simple, hard and fast rule. The model calculates a TWI score for every single point on the map. If that score is above 12, it's a no-go zone. The ground is just too unstable. It's excluded. No questions asked.
And then, of course, there's the big one, landslides. But again, we're not just guessing. The model actually uses historical data, learning the unique combination of slope, rock type, and water that has caused landslides in the past. It then uses that knowledge to create a predictive risk map for the entire area. All right, now for the final layer. We've found spots that are buildable and can survive nature, but all of that is completely useless if they're a sitting duck for the enemy. This is the layer that takes this from a civil engineering problem to a piece of strategic, defense-grade planning.
So the first and most critical security question is about visibility. Can the enemy see your proposed location from their known observation posts or high-altitude ridges? Because if they can see it, they can target it. Concealment is everything.
And this is where the system gets really tactical. We plug in the coordinates of known enemy positions and run what's called a viewshed analysis. The computer literally calculates millions of lines of sight to generate a concealment map, showing us exactly where the terrain's natural blind spots are.
And then there's the other non-negotiable rule, a massive safety buffer. No permanent hub can be built within 30 kilometers. That's the typical effective range of modern artillery. So we draw this huge exclusion zone along the forward line, and anything inside it is automatically out. This isn't a suggestion, it's a rule of survival.
So now we've pushed our Mac through all three layers, terrain, hazards, and security. It's time to combine all the clues and see what we're left with. This is the big reveal in our detective story.
Think of this as the brain of the whole operation, a weighted overlay. All the factors that made it through our filters, things like slope, landslide risk, concealment, they're each assigned a weight based on how important they are. And notice what gets the highest priority: having stable ground and avoiding landslides. Everything else comes second to that.
This quote just nails the elegant logic of the whole thing. First, you get rid of all the places that are simply impossible, the spots that are too steep, too wet, or in range of attack. Then, for every single pixel of land that's left, you calculate a final suitability score based on that weighted formula.
But, okay, how do we know the model is actually any good? This is the proof. It's a validation score. Think of it like a grade on the model's report card. A score above 0.8 is considered excellent. It means the model's predictions, especially for something as chaotic as landslides, are highly reliable. It's not just guessing, it's a scientifically validated tool.
So after all that analysis, all that filtering, all that weighting, we get this: a clear, simple answer. The final map gives every piece of land a score. Any spot above 0.8 is a prime candidate for a major hub. Anything between 0.65 and 0.8 could work for a smaller micro hub. Everything else, rejected. It's how you turn an impossible problem into an actionable map.
You know, this entire process is an incredible fusion of geology, hydrology, and military strategy, and it leaves you with a really fascinating question. If we can apply this level of analytical rigor to find a safe spot in the Himalayas, what other seemingly impossible planning problems could we solve with the exact same approach?